It's my very great pleasure to introduce Dr. Charmaine Tam, who's an analytics translator and senior research fellow at the Northern Clinical School and at the Centre for Translational Data Science at the University of Sydney. Charmaine works at the much needed interface between health domain experts and data engineers and scientists. And so without further ado, I'm going to welcome Charmaine, who's going to be talking about the art and science of extracting meaningful information from electronic medical records. Thanks, Charmaine.
Thank you, Sally. Thank you for the introduction and thank you for the invitation to present our work. So today I'll be talking about electronic medical records. I'll be talking about the type of data that they capture, and primarily I'll be focused on the limitations of the secondary use of data in eMRs, particularly focusing on uncertainty with regards to data quality. I'll be doing this by sharing results from a proof of concept project, which where we used eMR records to measure quality and processes of care in a cohort of patients presenting with acute coronary syndrome. And finally, I'll finish by sharing some pragmatic solutions for ensuring data quality when using eMRs and thus reducing uncertainty in the data itself. So to start with, medical records provide a systematic documentation of a single patient's medical history and care across time within one particular health care provider's jurisdiction. So that can be in an acute care setting, it can be in community health or general practice. However, it is refined to that particular information system. And the record contains a variety of notes that are entered by different types of professionals, whether they're clinicians or consultants or nurses, etc. And it's also recording a myriad of data, so ranging from observations, medications and treatment, as well as test results and reports. And really the electronic medical record is an extremely rich resource. It's for the analysts working on the project, it's unlike any data that they've ever experienced and probably will ever experience working in analytics. It's primarily composed of structured and both unstructured data. So the structured data would be probably what many health researchers are familiar with, and that's the data that's reported in administrative data sets or claims and insurance data sets, so such as diagnosis codes and procedure codes. However, it also comprises an extraordinary amount of very rich, versatile, unstructured data. And this can be both in its digitized form. So for instance, electrocardiograms, which have been measured on a machine and then printed and then scanned, or it can also be born digital data, so data coming straight out of machines being uploaded into the electronic medical record. And as well, we have a vast amount of clinical documentation recorded during a patient's visit, as well as reports as well. And the idea of being able to harness this information for future use is not a new concept. This is a paper published in New England Journal of Medicine in 1965. And in that paper, they talked about the tremendous accumulation of data, the changing emphasis of medicine from acute to chronic problems, and the increased attention to detailed recording of clinical observations. And they recognized that it would be difficult to organize this information into a patient-centric view, but they also recognized the extraordinary, advantages and benefits that this would have for clinicians, quality improvement and research. And this continues to remain today, and there's continues to be many articles published about eMR data processing. So I'm going to share with you some findings from a proof of concept project that we did. It was called Speed Extract, and we were focused on patients with STEMI, which is a type of acute coronary syndrome and a type of heart attack, serious heart attack. The primary aim of this project was really to demonstrate the feasibility of whether we could actually use this data in eMRs to accurately identify these patients from the system, and then whether we were able to use this data to measure some clinical indicators to measure processes of care. So pertinent for this presentation, the information required for a STEMI diagnosis is the clinical presentation, so the symptoms that you present with, which is usually presented in free text in clinical documents, troponin changes, which is a type of pathology test, and also an ECG finding. So for those of you who haven't worked with electronic medical records before, this is a visual representation of what it looks like coming out from being extracted from the database itself. And I guess it looks a bit like spaghetti. The two main tables are encounters tables and patient tables. The patient level information includes information about the patient's family history, medical history, social history, and then the information about the presentation itself is stored in the encounters table, and all the information that's collected from a single visit is linked back to this encounter table. So things like the type of procedures the patient had, the diagnoses that they have, so that could be an administrative ICD and administrative code, or it could be a diagnosis that a clinician records in a structured field. Plenty of forms. So in this particular eMR system, there's over 300 types. All the pathology results, scan documentation. So for instance, in this particular local health district, the the ECGs are scanned, printed and scanned in. And as well as many types of notes, so progress notes and assessments, etc. So this just kind of gives you, I guess, the breadth of information that we're dealing with. And in order to be able to, I guess, derive insight from that, we have to turn all that information into a patient-centric format. So this is kind of where the uncertainty around data quality comes in. Around using the secondary use of data in eMRs. For those of us working in health research, we're probably more used to working within traditional clinical research designs, such as RCTs or cohort studies and registries. And the benefits of this are that the data is collected in a very standardized way using standard methodologies, and therefore the data quality is high. However, some of the downsides of this approach are that the findings have limited generalizability, so restricted to that particular study cohort, and also the data is rarely reused. In contrast, in real-world EMR studies, the findings have high generalizability, they're cheaper, faster, and scalable, so the data is collected in every patient. The data is being reused for multiple purposes. However, it is unreliable, and that's because, as we've discovered, there is limited to no documentation about how that data is being collected, entered, interpreted, linked, etc. And I think one of the strongest points for using the secondary use of data in eMRs is that currently, with current traditional research, clinical research designs, cases are selected based on a disease diagnosis and then within that diagnosis, they're used to estimate the probability of symptoms given a particular disease. Now, because we capture the whole patient cohort, what this allows us to do in speed extract and other EMR studies is that we're able to determine the probability of the diagnosis given the presenting symptom, and that's the problem that clinicians want to know. So the first step to this process is being able to identify all the potential presentations of people who present with a particular condition. And in this case, it was people with a possible acute, a STEMI. And in order to do that, we had to cast a very wide net. And here you can see an upset plot of how we identified all the patients that presented with possible acute coronary syndrome. We weren't just interested in those that presented with a disease diagnosis of a STEMI, but we're interested in looking for potentially missed cases. And so here we've looked at people presenting with a broad range of symptoms. We've looked at people who've had a scanned ECG as part of their presentation. And here the goal of this initial identification was we wanted to identify a large pool of patients that could be potentially diagnosed as a STEMI. And so this is the reason we did this. It's because, and this figure verifies this, is that by design, very few of our presentations did have an ICD-10 code of STEMI. So here, these are each of our inclusion criteria that we used, and you can see that there's a very small component of each particular inclusion criteria that had the relevant diagnosis code. In another example, if we tried to identify patients with chest pain using their diagnosis code, you can see, for instance, in this particular group that presented with high likelihood of cardiac-related chest pain, that this condition isn't always recorded, and we do have to rely on the text in order to identify our cohort. And really, this represents the value of being able to extract data from the eMR and being able to utilize all the information, including the rich free text. And again, for more heterogeneous conditions, this is very important because diagnosis codes aren't necessarily used, or they're used in different ways. And so this is again another example where you can see the distribution of symptoms for patients presenting with severe mental illness and the variation in codes that each of these symptoms is associated with. Another issue with working with electronic medical records is that the data may not be correct, may not make sense. So this is an example of admission and discharge times from hospital, and what we've kind of had to engineer in order to turn the data into a more patient-centric way. So for instance, here you can see presentations to a single hospital, and they have a straightforward admission and discharge. Here we can see patients who are present to one hospital and are transferred to different hospitals, and you can see there's no overlapping timestamps. However, here what you can see is patients who are transferred two different hospitals, but we can see that the data tells us that they look like they're in two different places at the same time. So obviously we have to take this into account. They're not in two places at the same time, but really it's revealing that there are process issues with the data that have to be accounted for. So to validate our diagnosis code, we performed a validation study. And the reason for this is that diagnosis codes are not entirely reliable against clinician diagnosis. And so what we did was we collated clinically meaningful information, which was prepared, which was put into a user interface, and then we had 4 junior clinicians review about 900 cases of patients with potential acute coronary syndrome. And the aim of this was to develop a labeled data set that could be used to train algorithms to identify real STEMIs. Interestingly, what we found was that the agreement between the ICD code and the clinician diagnosis was over 90%. And so the codes themselves were able to accurately identify patients with a STEMI. However, when we also did the same study in more heterogeneous conditions, so another form of acute coronary syndrome, such as called NSTEMI, we found that there was variability, more disagreement in this process. And so the ICD-10 codes themselves, depending on the type of condition, may be agreeable with the clinician diagnosis, but in other conditions which are more heterogeneous, the sensitivity decreases. One of the other things that we did was looked at clinical care standards and whether we're able to use routinely collected data to measure some of these care standards. So for acute coronary syndrome, some of the points that they're interested in is whether you've received an ECG within 10 minutes of arrival to a hospital. And that's the one that I'll focus on today. And I guess this is really talking about highlighting uncertainty within information retrieval processes. So in this particular local health district, we were working with digitized images, and we were interested in extracting out the timestamp for the particular ECG. Some of the challenges for this was that there's a huge variation in ECG machines in ambulance and inpatient settings across the local health districts. We had to develop specific algorithms for extracting the text out of all these particular different algorithms, all these different ECG machines. The quality of the image was variable, and all this leads to potential loss of information. And so we were able to determine one of the indicators, which was time to ECG, and we were able to determine the proportion of patients who self-present and who do receive an ECG within 10 minutes of arrival, which is what the clinical indicator recommends. However, these results were affected by incomplete data extraction. And so I guess these sorts of measurements and insights have to be considered in the context of the way that the data is examined and processed. So to close, I wanted to finish with some pragmatic processes to ensure data quality. The way that we did this was that we worked very closely with a multidisciplinary team. We worked with clinicians every 2 to 4 weeks who review the data coming out from the eMR. And checked it for face validity. So we have ongoing data checks throughout the data extraction process, throughout the data linkage and the rearrangement of all the raw data tables within the eMR. Because of the nature of the data itself, it means that I guess applying standard statistical techniques for data cleaning have to be done very carefully. So for instance, outlier detection is tricky when results have to be interpreted in context. So for instance, high blood pressure can occur in the context of pain. It can also occur in the context of hypertension. Troponin, which is a measure, secreted and measured during a heart attack, can also be secreted in other other conditions as well. And finally, the data may also not be recorded. It may be imperfect, and we may not see it may not be recorded, so we do have to bear that in mind. So some of the other techniques that we use is that we plot all the timestamps, again, admission and discharge. We document everything that we do in version control. And I think most importantly is that we check the face validity of this data with local and senior clinicians and use, I guess, existing manual registries or manual audits to verify that this information is correct. And I'd like to thank the Speed Extract team. Thank you.